So with this lecture, we'll be moving to the next topic, which is memory management strategies. So we'll be discussing this topic under these headings. First, we'll be discussing introduction or background about the memory management strategies. And then we'll be discussing a concept called swapping. And then we'll be discussing contiguous memory allocation, then segmentation, paging, and then structure of the page table. So these are the topics we'll be discussing uh, under this heading, memory management strategies. So the objective of this particular topic is to provide a detailed description of the various ways of organizing memory and also to discuss various memory management techniques like paging and segmentation. Let us start with the introduction. So as you know already, before executing if you want to execute a program or a process, the program must be first brought into the memory from disk. Originally the program will be residing in the disk, and whenever it is to be executed, it should be brought into the memory. Once it is brought into the memory, then we will not call it as program, rather we'll be calling it as process. And CPU can only directly access the main memory and the registers. CPU can only directly access the main memory and the registers. CPU cannot access directly the hard disk or any other devices. Okay, that should be accessed through the respective controller. Okay, and memory unit can only see the stream of address or read request, address data and write request. Only these things memory unit can see. This memory unit basically don't know how these addresses were generated, who is generating, all these it don't know. It only knows which address to be referred, whether it should be read or it should be written. Okay, that is what the memory controller knows. Okay, every device will have a controller. Memory will have a controller. So here memory unit, in the sense the memory controller, can see only the stream of addresses, whether it is a read request or a write request. uh, Only this information it knows. It do not know anything about like how these addresses were created. If some data is uh, available in CPU in the registers, okay, so registers are the one which CPU can access very fastly, because registers are present inside the CPU itself. So the processor or the CPU can access the register very quickly. It can access the register uh, in less than one clock cycle. Okay, it can access the register in less than one clock cycle. Okay, so if CPU want to perform some operation on the data that is stored on the registers, then CPU can do that at a very faster speed. It can do at the rate of more than one operation in a single CPU clock cycle. Okay, so the point here I'm trying to make is, if some data is present inside the CPU registers, and if CPU want to perform some operation with that data, then CPU can perform such operations, not one operation, it can perform more than one operation within a single clock cycle. Okay, but this is not the case with main memory. But this is not the case with main memory, because CPU cannot CPU can access the main memory only through through buses. Buses are nothing but communication channel. There will be some address bus or data bus. Only through this bus the CPU can access the memory. Okay, so it will take some time. It will say take some time to access the data that are stored in the memory. Okay, so typically, if CPU requests some data from memory, and by the time the data reaches to CPU, it may take many clock cycles. It cannot do, it cannot get a data from memory within one clock cycle. No, it may take several clock cycles. But that is not the case with the data that is stored in registers. CPU can perform operation on the data that is stored in registers in less than a clock cycle. So CPU basically can perform more than one operation on the data that is stored on registers within a single clock cycle. But that is not the case with memory, because memory are accessed through buses, and and it will take some time for the CPU to get the data. So maybe it may take more than one clock cycle. So completing a memory access may take many cycles of the CPU clock. Okay. So in such cases, the CPU should stall. Stall in the sense it should halt or it should wait. In such cases, the CPU should halt because what it can do without the data, it want to perform some operation, like it may want to add something or it may want to multiply, but until the data comes, it cannot do anything. So during that time, the CPU should stall. Okay, but this stalling of CPU is not tolerable. Okay, this stalling of CPU is not tolerable because there will be many such memory access. Because there will be many such memory access. It is not just one access. When a program is getting executed, many times CPU may have to get something from the memory. So every time if it stalls, then the CPU resource is not getting utilized effectively. Okay. To avoid such CPU stalls, cache memory is introduced. So you know about cache memory. Cache memories are high speed memory that are placed in between main memory and the CPU. Okay. So there are two types of cache, internal cache and external cache. If it is an internal cache, then this will be placed inside the CPU itself. If it is an internal cache, then it will be placed inside the CPU itself. In that case, CPU can access those data very quickly. Okay. So only if the data is not in the cache, it will refer the memory. Okay. So only whenever it is accessing the memory, during that time only the CPU may have to stall. Other times it need not stall. Okay. Okay, fine. So we are not only concerned with the speed of accessing the memory. Here we are not only concerning about the speed of accessing the memory, but we are also concerned about the memory protection. Protection in the sense, as we already know, different user processes will be stored in different locations in the memory. Okay, different user processes will be stored at different locations in the memory. So every user process will have a certain limit of memory. They can access only those locations. They cannot access beyond that. So if a user process is allocated some amount of memory, some X amount of memory, he can access only that much. He cannot access anything beyond that. Okay, so this should be ensured. So this is called as uh, pro- this is called as providing ensuring correct operation. Okay, so we are not only concerned with the relative speed of accessing the memory, but we must also ensure correct operation. We should ensure that the user is not the user program, especially when the process is in the user mode. It should not be allowed to access beyond its location. Okay, so let us assume, say this is for process 1, this is process 1, say this is process 2. Okay, and this is process 3. So it means what? Process 1 can access any memory contents between here and here, but it cannot access anything beyond that. Similarly, process 2 can access only memory contents between these locations. It cannot access anything beyond. Similarly, process 3 can access only memory contents between this location. It cannot access anything beyond that. So this should be ensured. How it will be ensured? So this will be ensured by using two registers. These are base and limit registers. These are base and limit register. So base register will hold the starting address of the memory from which the CPU, from which this particular process can access. It will hold the starting address of the memory from where this particular process can access. And a limit register will hold the length starting from this location, how much location it can access. That will be stored in limit. Okay. So you can see here the starting location is 3,40,000, the memory address, and the ending location is 1,20,900. So it means that this particular process P2 can access starting from the location 3,42,000 3,42,000 4,20,940. Okay, because just add this with 12,940. Okay, sorry, 1,20,900. So that is the this value you will get. Okay, so the limit register does not contain the end address, it contains how much locations it can access. Okay, so this is how the correct operation or memory protection is ensured. Okay, this will be taken care by hardware. This will be taken care by hardware. This will not be taken care by the operating system. Okay, operating system will only do one thing. Operating system job is to load the correct values in the base register and the limit register. Okay, and when doing that, operating system will obviously do that in the kernel mode, because user programs cannot access the base registers and limit registers. It can be accessed only in the kernel mode, right? Because user programs have some limit like what they can perform, but there is no limit with respect to the kernel processes, right? So this is how correct operations of memory is ensured. Okay, right. And this is how the hardware uh, ensures that the process is accessing the correct address. So whenever CPU says that I want so and so memory location should be accessed, so this hardware based protection logic, what it will do in the sense, hardware address protection, what it will do in the sense, it will check whether the address that is requested by the CPU for this particular process PI, is it greater than or equal to the content of the base register or not. Yes, if it is yes, it will go next. Then it will check whether the address is less than the base plus limit content or not. Yes, then it can access, otherwise it cannot access. If anywhere no comes, then a trap will be created. Then a trap will be created to the operating system, stating that there is an addressing error. Okay, then a trap will be created stating that there is an addressing error, right? So this is how the memory controlled access to the memory or protection or correct operation of memory is ensured. Fine. Now let us move to a next important concept, which is called as address binding. So as we have already discussed, initially all the programs will be residing in the disk, and then depending on the requirement, it will be brought to the main memory. The programs which are on the disk and they are ready to be brought into the memory, the programs which are in the disk and they are ready to be brought into the main memory will be stored in a queue, and that queue is called as input queue. The program that are in the disk and that are ready to be brought into the memory will be stored in a queue, and that queue is called as input queue. Okay, see, it is not that always the first process will be loaded at the address 000. Obviously memory address will start with 000, okay, and it will end with some address. Okay, but it is not that the whatever the first process loaded, it will come to 000. No, that is not the case. It depends. Wherever the memory is free, the operating system can allocate location for the process at any place. Okay, so this is just for information. Okay, now what we'll be discussing is there are before defining address, before officially defining address, first let us understand that there are different types of addresses available. So what are the different types of addresses? Okay, let us understand that from operating system point of view. Okay, right. So so okay, there are different types of addresses available. The addresses that are available in the source code, that is in a program, these addresses are called a symbolic address. The addresses that are available in the source code or in the programs, these addresses are called a symbolic address. What do you mean by symbolic address? Say for example, you are writing a C program or a Python program, and there you are saying that uh, int x equal to 10, okay, or or y equal to 100, okay, comma y is equal to 20, like that we are defining some variables, right? So these variables are nothing but symbolic addresses. Not only variables, variables, object, anything the user defines which needs a memory location. Anything the user defines and that needs a memory location, that is nothing but symbolic address. So X is a symbolic address, Y is a symbolic address, or if you define a string, say it's a Java program, you are declaring a string. Now the string is object, okay? String, uh, uh, okay, X is, so say x2, string x2 is equal to something we are storing, say CSE. Now this x2 is a symbolic address, okay? So basically any variables that you declare, or anything, it may be an object, uh, or any other thing that needs special memory and that is defined by the user, all these comes under symbolic address, okay? So the source code uses what in the sense, the source code usually represent things using symbolic address. Here we don't use any numbers, right? Actually for X in the memory there may be some address 7000, but here we don't use 7000. We always say X. This is X. This is Y. The string X2, like that only in the program we refer. So referring the values through some symbols, that is called a symbolic address, right? Fine. Okay. During uh, compiled code, so compiled code, what it will do in the sense, it will bind the symbolic addresses to relocatable addresses. After compilation, after compilation, this symbolic address will be binded to relocatable address. What does it mean? Say hereafter X will not be referred as X after compilation. You may call X with an address 000. 000 will refer X. Okay. Y may be referred with an address. Y may be referred with an address 0010. 0010. I'm telling some example. Okay. X2 may be referred with some other address, say 0020. So after compiling, this symbolic address will be converted to a relocatable address. After compiling, the symbolic address will be converted to a relocatable address, right? After linking, after linking, or loading, the relocatable address will be converted to absolute address. After linking or loading, the relocatable address will be converted to absolute address. What does mean by absolute address? How? Okay, so symbolic address to relocatable address is fine, because some symbols, this each symbol some address is given, right? That is okay. Okay, but what do you mean by what do you call, what do you mean by absolute address? So after linking and loading, what happens in the sense, this symbolic, this relocatable address will be converted to absolute address. What does it mean? See, after linking and loading only, you will be knowing like which location this process will take. What will be the starting location of this process? What will be the starting location of this process? So that will be determined by which register? That will be determined by the base register. So if, let us assume that, so this particular process, whatever the process we are discussing right now, it is going to be loaded in the location 4000. That is, its base register is 4000. It is going to be loaded starting from the location 4000. We are not bothered about limit register now. Okay, you can assume some limit register as 100. So if you assume limit register as 100, then this process will be stored starting from 4000 to 4100. Okay, right? So now from this, what you call, from this relocatable address, absolute address will be calculated. For that, what you should do in the sense, add the relocatable address with the content of base register. Add the relocation address with the content of base register. So then you will get the absolute address. So to get the absolute address for X, to get the absolute address for X, add its relocatable address with the content of base register. What is its relocatable address? 000. Its base register is 4000. So 4000 plus 000 is 4000. Okay. So this is the absolute address of x. Similarly, to get the absolute address of y, add its relocatable address with the content of base register. It is 4000 plus 10, which is 4010. Similarly, to get the what you call absolute address of x2, add the content of the base register with the x2's relocatable address. Okay, so what you get is 4000 plus 20, which is nothing but 4020. So this is how we convert the uh, this is how the relocatable address are converted to absolute address, right? I think it's clear. So the addresses that are used in the source code or in the high level programming languages, those are called a symbolic address. In fact, they are not address, they are some symbols, some variables, x, y, object name or anything. Okay. After compilation, these addresses will be converted to relocatable address. Because after compilation, we don't know in which location it should be added. So some these relocatable address are also called as relative address. There is another term, relocatable address is also called as relative address, because it is not an absolute address, it is relative to something else. Okay, it is relative to what? It is relative to which location this process is going to be loaded. That will be decided in the runtime only. Okay, so after linking or loading, when the process is loaded at the memory, then you will get the base register address. Okay, so the absolute address will be obtained by adding the content of the relative or the relocatable address with the content of the base register, right? Okay, so here there is an example. If the relocatable address is 14 and the base register content is 7400, if the or 74,000, if the relocatable address is 14 and if the base register content is 74,000, then the absolute address will be 74,014, right? So this is, so basically binding means converting one address to another address. That is called as binding. Converting one address type to another address type, that is called as binding. Okay, fine. So let us continue our discussion. Fine. Okay, so this address binding can happen at three levels. Okay, so in the previous slide we have discussed three types of addressing. One is symbolic address, then the next one is relocatable address or relative address, and the next one is absolute address. Now what we are going to discuss is the binding of instructions and data to memory address can happen at three places. Okay, so binding is not only with data. In the previous example we discussed data x, y, x2, all these are data, but this binding also applicable to instructions. Instructions are program statements, because everything will be stored in the memory. Okay, so this binding can happen at three places. It can either happen at compile time, or it can happen at load time. Okay, or it can happen at execution time or runtime. Okay, first let us, what is compile time? Compile time means the time at which you are compiling the program. That is called as compiling. Okay, you may compile but you may not execute. You may compile but you may not execute it. Okay, so if the binding that happens at during compilation, that is called as compile time binding. The binding that is happen at load time, that is uh, while loading, actually compile time and load time is related. We will come back to that later. Okay, so let me not define load time now. Okay, I'm not defining load time now, because these two are related concepts, compile time and load time binding. Okay, if the binding happens at runtime or execution time, then that is called as execution time binding. Okay, fine. Now let us see what is these three types of binding are. First is compile time binding. What is compile time binding? Say, say if the memory location to which you are going to load the program, if the memory location to which the program is going to get loaded, if it is known already, that is, if it is known during the compile time itself, okay, then during the compile time itself, absolute code can be generated. or absolute address can be generated, and such binding is called as compile time binding. Is it clear? If the memory address to which the program should be loaded, if it is known during the compile time itself, if the memory address to which the program will be loaded, if it is known during the compile time itself, then during compilation itself, absolute address or absolute code can be generated. So that type of binding is called as compile time binding. Okay, right? So but if you don't know the memory address during compilation time at where the program should be loaded, at where the process should be loaded, okay, then you cannot go for absolute binding. Then what binding will happen in the sense, then it will happen, then there will be relocatable binding. Okay, so relocatable code will be created. Relocatable code means relative addressing. Okay, relocatable code will be created if memory location is not known at compile time. Here memory location means starting memory location where the process is to be loaded. If that is not known during compile time, then relocatable code will be generated. Okay, if memory location is known already, if memory location is known before the compile time itself, then absolute code will be generated. Okay, okay. So to elaborate further, assume that there is a C program .c. Okay, you have written this program, say abc.c. Okay, you are going to compile this program. Okay, say before compilation itself, before compilation itself, the compiler got the information that after compilation, this program can be loaded starting from the location 2000. Then what it will do, all address it can generate as absolute address, because it knows its starting address well ahead. Before compilation itself, it knows the starting address. So it will, whatever the address it will create will be an absolute address. Okay, say as we discussed in the previous case, there are variables x, y, and x2. So for x, it will create the address 2000 plus 0, which is 2000. Okay, because it knows the starting address. For y, it will create the address 2000 plus 20, which is 2020. Okay, and for x2 it will create 2000 plus 10 for y, 2010, and for x2 it will create an address 2000 plus 20, that is 2020. Okay, because it knows where it should be loaded, so directly in the compile time itself the absolute address is created. Okay, but say you are compiling this program abc.c, but before compilation the compiler was not given this information like where it will be loaded. Compiler is not given this information. Now compiler don't know after compilation, during execution, or before execution it should be loaded. uh, where it should be loaded, that it don't know, but still it want to compile. So it will compile using relocatable address. So now it will assume x address as 000. Okay, that is a relocatable address, because we don't know what is the base address or the starting address. And y address it will assume as 0010. Okay, and x2's address it will assume as 0020. So that is called as uh, relocate relocatable code. Okay, that is called as relocatable code. Okay, now when this relocatable code will be converted to absolute code, during load time. During load time it will be converted to absolute code, because if during compilation time if you don't know the address where it should be loaded, then it will create a relocatable code, and this relocatable code will be again converted to absolute code during load time. Whenever it is loading, at least during loading, it should be informed, right, where at which location it should be loaded. So at that time it will be converted. Okay, so this is about compile time and load time binding. That is, before compile time itself, if you know, if the compiler was given the information about the base address or the starting address where the program should be loaded, then the compiler itself will create directly absolute code. If the compiler was not given this information, then the compiler will create a relocatable code. Okay, will create a relocatable code, right? And then the third thing is binding at execution time. So what is binding at execution time? So why, so at least you should bind at load time, because loading you should know, right? So what is binding at execution time? In the sense, sometimes binding will be delayed until execution time or runtime if the process can be moved during its execution. The process can be moved during its execution from one memory location to another memory location. Okay. So if the process can be moved during execution from one location to another location, then the binding will happen only at execution time. Okay, that is the actual absolute address will be known only during the execution time. Okay, so these are the different types of binding uh, of instructions and data to memory. Okay, fine. So so this particular diagram, it shows like it shows a brief overview of the process execution. So here is the source program, then it is compiled or assembled. Okay, after compiling, it is converted to object code. Then it is linked. Linked means combining with other object code. Maybe this is one module, there may be another module of your program, or there may be 10 modules. All the 10 modules should be connected. That is what the linking does. Linking will connect other modules in object code format. Okay, then it will be loaded into memory. Okay, and that will be done by the loader. So loader, while loading, loader may also include uh, the system libraries, because sometimes you may use some system library also in the program. For example, in C you may use math.h. Your program might have included the header file math.h. It is a library, right? And from math.h you may be using some function. You may be using sine function, you may be using cos function, you may be using power function. Where are those codes? Those codes also should be connected. So that will be done by the loader. Loader will connect your code, the system library. Okay, right? And then the memory, then it will be loaded into the memory. Okay, this connecting with the system library can happen at two times. Either it can happen during runtime. Okay, so that is called as dynamic binding. After loading, after during execution also, this connecting may happen. That is called as dynamic binding. Okay, or sometimes before execution it may happen. That is called as static binding. Okay, that we shall discuss in the coming lectures. Fine. Let us stop here with this. Thank you.